Hello, everyone, and welcome to our lesson on summarizing data. In today's world, we are surrounded by vast amounts of information, or data. To make any sense of it, we need tools to condense it into a few meaningful numbers and graphs. By the end of this lesson, you will be able to organize data using frequency distributions, calculate and interpret measures of central tendency and dispersion, identify any unusual data points called outliers, and understand how simple changes to the data affect our summary statistics. These skills are fundamental to the field of statistics and are used everywhere, from scientific research to business analytics. Let's start with a real-world problem to see why statistical estimation is so powerful. Imagine you are an ecologist, and you want to estimate the total number of cod in the North Sea. It's impossible to count them all, right? So we use a clever method called capture-recapture. First, the ecologists capture a large number of cod, say 50,000. They tag them in a harmless way and then release them back into the sea. After giving the tagged fish enough time to mix back in with the general population, they take a second sample. Let's say 6 months later, they capture 40,000 cod. And of these, they find that 20 are tagged. Now, how can we use this information to estimate the total population? We can make a key assumption. We assume that the proportion of tagged fish in our second sample should be roughly equal to the proportion of tagged fish in the entire North Sea. This is a reasonable assumption if the tagged fish have mixed thoroughly. So we can set up a proportion. Let n be the total cod population we want to find. The ratio of the initially tagged cod to the total population, which is 50,000 over n, should be equal to the ratio of tagged cod in the second sample to the total size of that sample, which is 20 over 40,000. Now we just have to solve this equation for n. First, we can simplify the fraction on the right. 20 divided by 40,000 is 1 over 2,000. Now we can cross-multiply to solve for n. n equals 50,000 times 2,000, which gives us an estimate of 100 million cod in the North Sea. So you see, we've estimated a huge number without counting every fish. Of course, this estimate depends on some important assumptions. We assume the population is closed, meaning no significant number of fish entered or left the area, and that being tagged doesn't make a fish more or less likely to be caught again. The validity of our statistics often rests on such assumptions. Now, let's move on to one of the most fundamental ways to organize data. We'll talk about frequency distributions. A frequency distribution is simply a table that lists all the possible values or categories in a dataset, along with how many times or the frequency each one appears. It's a way of tidying up raw data. Let's look at an example. This table shows the time, recorded to the nearest minute, that a group of students took to complete an IQ test. The top row is the time in minutes, and the bottom row is the frequency, which means the number of students who finished in that time. For instance, if we look at the column for 4 minutes, we see a frequency of 12. This means 12 students took exactly 4 minutes to complete the test. First question, how many students took the test in total? To find the total number of students, we just need to add up all the frequencies. We are summing the number of students for each time category. So we sum 1 plus 2 plus 5, and so on, all the way to the last frequency of 1. Adding these all up gives us a total of 67 students. Sometimes we have too many individual data points, and it's more useful to group them into classes or intervals. Part B asks us to summarize this information into a new table with wider time intervals. Notice the intervals, 0.5 to 3.5, 3.5 to 6.5, and 6.5 to 10.5. Why these strange boundaries like 0.5 and 3.5? The problem states the times were recorded to the nearest minute. This means a time recorded as 3 minutes could be anything from 2.5 up to, but not including 3.5. These are called continuity corrections. So, the first interval, from 0.5 up to 3.5, will include all students whose recorded times were 1, 2, or 3 minutes. To find the frequency for this group, we add their individual frequencies, 1 plus 2 plus 5, which equals 8. For the second interval, from 3.5 up to 6.5, we include the recorded times of 4, 5, and 6 minutes. The total frequency is 12 plus 16 plus 14, which is 42. Finally, for the interval from 6.5 up to 10.5, we include the times 7, 8, 9, and 10 minutes. Adding their frequencies gives us 10 plus 4 plus 2 plus 1, which is 17. And here is our completed summary table. Notice that if you add the new frequencies, 8 plus 42 plus 17, you get 67, which is the total number of students we found earlier. This is a good way to check your work. Once we've organized our data, we often want to find a single number to represent the center or typical value of the data set. These are called measures of central tendency, or more commonly, averages. There are three main types of average we'll use. First is the mean, often shown with the symbol X bar. This is what people usually think of as the average. You add up all the numbers and divide by how many numbers there are. Second is the median. To find the median, you must first put all the data values in order from smallest to largest. The median is the one right in the middle. And third is the mode. The mode is simply the value that shows up more often than any other value. A data set can have one mode, more than one mode, or no mode at all. Let's calculate these for a simple data set. While you can often use your calculator, it's important to understand how they are calculated. Consider the data set 1, 1, 3, 6, and 8. To find the mean, we sum the values. 1 plus 1 plus 3 plus 6 plus 8 equals 18. There are 5 values, so we divide 18 by 5, which gives us a mean of 3.6. For the median, we first order the data, which it already is, 1, 1, 3, 6, 8. With 5 values, the middle one is the third value, which is 3, so the median is 3. If you have an even number of data points, the median is the average of the two middle values. For example, if we had the data 1, 1, 3, 6, the two middle values are 1 and 3, so the median would be 1 plus 3 where 2 equals 2. Finally, for the mode, we look for the most frequent value. In the set 1, 1, 3, 6, 8, the number 1 appears twice, while all other numbers appear only once. Therefore, the mode is 1. It's important to consider which measure of average is most appropriate. The mean is sensitive to extreme values, while the median is not. The mode is most useful for categorical data. Let's dive a bit deeper into calculating the mean, especially when we have unknowns in our data. Remember, the formula for the mean X bar is the sum of the values, which we denote with the Greek letter sigma, x, divided by the number of values, n. We can use this formula algebraically. Let's try an example. Suppose we are told that the mean of the 6 values 1, 2, 4, 5, a, and 2a is 8. Our goal is to find the value of a. We'll start by plugging everything we know into the mean formula. We know the mean X bar is 8. The number of values n is 6. The sum of the values sesx is 1 plus 2 plus 4 plus 5 plus a plus 2a. Combining the constant terms and the a terms, the sum is 12 plus 3a. So our equation is 8 equals the quantity, 12 plus 3a, all divided by 6. Now we just need to solve this equation for a. First, multiply both sides by 6 to get 48 equals 12 plus 3a. Then subtract 12 from both sides, which gives us 36 equals 3a. Finally, divide by 3, and we find that a equals 12. This same principle applies when our data is in a frequency table. Let's look at this frequency table. We're told the mean of this dataset is 4.2, and we need to find the unknown data value y. To find the sum of all values, we must multiply each data value by its frequency. For example, the value 1 appears 4 times, so it contributes 1 times 4 to the total sum. First, let's find the total number of data points, n, by summing the frequencies. 4 plus 5 plus 8 plus 3 equals 20. Now we set up the equation for the mean. 4.2 equals the sum of value times frequency for each column, all divided by the total frequency, 20. Let's simplify the numerator. 1 times 4 is 4. 2.5 times 5 is 12.5, 6 times 8 is 48, and y times 3 is 3y. Adding the known numbers, we get 64.5. So our equation is 4.2 equals 64.5 plus 3y over 20. To solve for y, we multiply both sides by 20, giving 84. Then we subtract 64.5 from 84, which leaves 19.5. Finally, dividing 19.5 by 3, we find that y equals 6.5. What happens when our data is already grouped into intervals? We can't calculate the exact mean because we don't know the individual data values. However, we can find a very good estimate for the mean. The method is to assume that all the values in an interval are centered around its midpoint. So we use the midpoint of each class to represent all the data in that class. Let's take this frequency table of grouped data. We want to estimate the mean value. First, we need to find the midpoint for each interval. The midpoint is just the average of the lower and upper bounds of the interval. For the first class, it's 0 plus 4 divided by 2, which is 2. For the second, 4 plus 10 divided by 2 is 7. And for the third, 10 plus 20 divided by 2 is 15. Now we have a new table with midpoints and frequencies, and we can calculate the mean just like we did in the previous example. We multiply each midpoint by its corresponding frequency, sum these products, and then divide by the total frequency. The total frequency is 15 plus 35 plus 50, which is 100. The numerator becomes 30 plus 245 plus 750, which is 1025. So our estimated mean is 1025 divided by 100, which is 10.25. Remember, this is an estimate because we used midpoints instead of the actual data values. When dealing with grouped data, we also can't find a single mode. Instead, we identify the modal class. The modal class is simply the interval that has the highest frequency. It's the most common group. In this example, we look at the frequencies 6, 14, and 22. The highest frequency is 22. Therefore, the modal class is the interval corresponding to this frequency, which is 18 is less than or equal to x is less than 22. Besides the center of the data, we are also very interested in how spread out the data is. This is measured by measures of dispersion. We'll start with quartiles and the interquartile range. Just as the median splits the data in half, quartiles split the data into quarters. First, you must order the data. The first quartile, Q1, is the value that separates the bottom 25% of the data. The second quartile, Q2, is just another name for the median, and the third quartile, Q3, separates the bottom 75% from the top 25%. Let's find the quartiles for this data set. The data is already ordered. There are 6 data points. The median, or Q2, will be the average of the 2 middle values. The 2 middle values are 5 and 5, so the median is 5 plus 5 divided by 2, which is 5. Now to find Q1, we look at the lower half of the data, which is the set 3, 3, 5. The median of this smaller set is 3. So Q1 is 3. To find Q3, we look at the upper half of the data, 5, 12, 15. The median of this set is 12. So Q3 is 12. Now that we have the quartiles, we can calculate our first measure of spread. The interquartile range, or IQR, is the distance between the third and first quartiles. It tells us the range of the middle half of our data, which makes it resistant to the effects of very high or very low values. For our example, Q3 was 12 and Q1 was 3. So the IQR is 12 minus 3, which equals 9. This means the middle 50% of the song lengths in this dataset span a range of 9 minutes. While the IQR is a useful measure of spread, the most common and powerful measures are the standard deviation and variance. Let's talk about standard deviation and variance. The standard deviation, represented by the Greek letter sigma, gives us a sense of how far on average each data point is from the mean of the dataset. A small standard deviation means the data points are all very close to the average. A large standard deviation means the data points are widely spread out. The variance is simply the standard deviation squared. It's also a measure of spread, and it has some important mathematical properties that we'll see later. For now, just remember that variance is sigma squared. The formulas for these are quite involved, but the good news is you will almost always use your graphing calculator to find them. Let's take this example of 10 egg masses. We'll find the standard deviation, variance, and interquartile range using the values from a calculator. After entering these 10 values into a list on your calculator and running the one variable statistics function, you would find that the standard deviation, often labeled as sigma x or sigma x, is approximately 3.98 grams. This tells us a typical egg's mass is about 4 grams away from the average mass. To find the variance, we square the standard deviation. Squaring the more precise value from the calculator, 3.97995, gives us approximately 15.8. The units would be grams squared, which is a bit strange, and it's one reason we often prefer to talk about the standard deviation. The calculator also gives us the quartiles. The calculator output shows that the first quartile Q1 is 64 grams and the third quartile Q3 is 69 grams. So the interquartile range is Q3 minus Q1, which is 69 minus 64, giving us an IQR of 5 grams. The middle 50% of the eggs have masses within a 5-gram range. Sometimes a dataset contains values that are unusually high or low compared to the rest of the data. These are called outliers. It's important to identify outliers because they can heavily skew our statistical results, especially the mean. We have a formal mathematical rule for flagging a data point as an outlier, and it uses the interquartile range. A data value is considered an outlier if it falls more than 1.5 times the IQR below the first quartile or more than 1.5 times the IQR above the third quartile. Think of these as fences. Anything outside the fences is an outlier. Let's apply this rule to an example. Suppose a dataset has a lower quartile of 60 and an upper quartile of 70. We want to find the boundaries for outliers. The first step is always to calculate the IQR. The IQR is Q3 minus Q1, so that's 70 minus 60, which is 10. The spread of the middle half of the data is 10 units. Now we calculate the lower and upper fences. The lower fence is Q1 minus 1.5 times the IQR. That's 60 minus 1.5 times 10, which is 60 minus 15, giving us 45. Any data point below 45 is an outlier. The upper fence is Q3 plus 1.5 times the IQR. That's 70 plus 1.5 times 10, which is 70 plus 15, giving us 85. Any data point above 85 is an outlier. So for this data set, any value less than 45 or greater than 85 would be officially flagged as an outlier. This rule gives us a consistent way to identify these unusual points for further investigation. A very important topic in statistics is understanding how our summary numbers change when we transform the data. For example, by converting units. Let's look at the effect of constant changes on the original data. We'll consider two cases: adding a constant and multiplying by a constant. First, what happens if we add the same number, let's call it k, to every single value in our dataset? The rule is that adding a constant k will shift the entire dataset. This means all measures of center, like the mean, median, and mode, will also increase by k. However, the spread of the data doesn't change. The data points are still the same distance from each other. So measures of spread, like the IQR and standard deviation, remain unchanged. For example, if a dataset has a mean of 12 and a standard deviation of 15, and we add 100 to every value, the new mean will be 12 plus 100, which is 112. The standard deviation, being a measure of spread, is unaffected and remains 15. Now for the second case, what happens if we multiply every value in the dataset by a constant k? When you multiply by a constant, you are stretching or shrinking the entire dataset. This affects both the center and the spread. The rule is that both the measures of center and the measures of spread get multiplied by that same constant k. Let's say a dataset has a median of 2.4 and an IQR of 3.6. If we have every data item, that's the same as multiplying by 0.5. The new median will be 2.4 times 0.5, which is 1.2. The new interquartile range will also be multiplied by 0.5, so 3.6 times 0.5 is 1.8. Both the center and the spread are halved. To wrap things up, let's tackle a common problem type: finding a combined mean from two different groups. This is a great application of the mean formula. Imagine one group of 12 students has a mean test score of 67.5, and another group of 10 students has a mean score of 59.3 on the same test. What is the mean score for all 22 students combined? A common mistake is to just average the two means, 67.5 and 59.3. But we can't do that because the groups have different sizes. We need to calculate a weighted average. The overall mean is the total sum of all scores from both groups divided by the total number of students. We can find the sum of scores for each group using the mean formula, sum mi mina n. For group 1, the sum of their scores is their count, 12, times their mean, 67.5, which is 810. For group 2, the sum of their scores is 10 times 59.3, which is 593. Now we can find the grand totals. The total sum of all scores is 810 plus 593, which is 403. The total number of students is 12 plus 10, which is 22. Finally, the overall mean is 403 divided by 22, which is approximately 63.77. Notice this is closer to the mean of the larger group, which makes sense. So today, we've covered a lot of ground in descriptive statistics. We've learned how to organize data in frequency tables, how to calculate and interpret measures of center and spread, how to identify outliers, and how data transformations affect these measures. These are the essential building blocks for understanding and communicating about data. Excellent work today. Keep practicing these concepts as they will be crucial for everything we do next in statistics.